Alright, so in this video we are solving a number of problems related to electrochemistry. So that's what we are doing. The first problem deals with predicting potentials. So we have the following half reaction, or the following half reactions: magnesium plus 2 electrons to give us magnesium solid. So you can see all these half reactions are reduction half reactions. Normally, when you are given half reactions, most of the time you will be given them in reduction form, where you are adding the electron to an ion. So the question is, which cell has the highest potential among the following? So in terms of potential, it's the same as which cell is likely to give you a chemical reaction. So if we say which cell has the highest potential, we mean which cell is most likely to give a chemical reaction. Now, if you are looking for that, the answer is the more positive E the cell has, the more likely it is to give a reaction. So the more positive E the cell has, the more likely it will occur, or it will react. Now let's see what we have. Here we have Fe2 plus and Mg solid, which means we are combining. So this is 1, this is 2, this is 3, which means we are combining 1 and 3. So we are combining 1 and 3. In this case, we can draw this cell as Fe2 plus aqueous. Yeah, let me redraw it again. So we start with oxidation and then reduction. So in this case, magnesium is being oxidized, iron is being reduced. So this cell can be written as Mg solid, Mg2 plus aqueous, because we start with oxidation. And then salt bridge, Fe2 plus aqueous, then Fe solid. So this part of the cell is anode, this part of the cell is cathode. That is, we are dealing with this cell. But we know that each cell is E cathode minus E anode. So in this case, our E cathode is the E that is given, or our E cathode is this one. The cathode is here. So this one is the cathode, which is minus 0.44 volts, minus our E anode is given by this one, minus 2.37 volts. So for that one, the voltage of that battery or that cell is plus 1.93 volts. So since this cell has given us positive voltage, the cell has given us positive voltage, it is spontaneous, because we know that when E is positive, the reaction is spontaneous. So really, the first reaction, this reaction is going to happen and it is spontaneous because we have E cell that is positive. So let's look at the second reaction. So I'll just delete this. So we see that the first reaction has a voltage of plus 193 voltage or volts. So here I will say E cell is equal to plus 193 V. Now let's go to the second one. The second one here is this reaction. What will be the E cell of this reaction? So when you look at this reaction, you need to determine which one is the anode, which one is the cathode. And also we first look at what is the combination to get to this reaction. So we have tin here from here, which means we take reaction 2 and then we have magnesium and reaction 1. So this one is a combination of 1 and 2. So these are the reactions we are combining. Now if you look at this reaction, the magnesium is being oxidized, so it is the anode. The tin is being reduced, so it is cathode. So in this case, we say the same thing. E cell is equal to E cathode minus E anode. In this case, our cathode is the magnesium cell, which is this one. not our cathode. Magnesium is undergoing oxidation, so it will be the anode. Tin is undergoing reduction, so it will be the cathode. So our cathode is the tin, which is 0.14 V, minus the anode, which is minus 2.37 volts. When we add the two, or when we subtract the two, we get a voltage of plus 2.23 volts. So that is 2.23 volts. So we can say that the voltage of reaction 2 is 2.23. So let me transfer that voltage to the second reaction. So we are saying for this reaction, the E cell for this is plus 2.23 volts. So immediately we see that this tin reaction is more spontaneous than the ion reaction, because the tin is more positive. Now let's look at the third reaction. So in this reaction, the ion reaction is the cathode and the tin is the anode, because tin is undergoing oxidation and the ion is undergoing reduction. So as usual, the E cell is given by E cathode minus E anode. In this case, our E cathode is minus 0.44 V, minus our E anode minus 0.14 V. So if we do the math for that, the answer is minus 0.30. So the third reaction, the E cell, is equal to minus 0.30 volts. So I'll get rid of this part. Now if you look at these reactions, you see that, so if this is A, this is B, this is C. In terms of numbers, you see that B has the highest potential. So B has highest potential, A has intermediate potential, C will not occur. So C is not spontaneous because it is negative. So the conclusion we can make here the more positive the cell reaction is, the higher the potential of the reaction. So you look at the E cell. So the more positive the E cell, the higher the potential. So based on our question, we will say that this second reaction has the highest potential. So the second reaction has the highest potential. Let's move on. So we have these reactions, half reactions. So the question is, identify the cathode and anode for the two half reactions. So identify the cathode and anode for the two half reactions. Now, for this one, we need to know a cathode is where reduction occurs. Anode is where oxidation occurs. So if we look at these two reactions, another statement that we need to make is the more positive E, the more positive half E is the cathode. So while the more negative half E is the anode. So if you want this reaction to be spontaneous, then the cathode should have more positive E cell and the anode should have more negative E cell. Now, coming back to this question, identify the cathode and anode from the two half reactions. So basically, this one is the cathode because it has more positive E cell. It has more positive E cell. This one is anode. It has more negative E cell. So if you are looking at the this cell, you want to write a reaction equation for the cell. It means you will start with the cathode here, which is undergoing reduction, and then you have ion which is undergoing oxidation to give you ion aqueous and then tin solid, because this undergoes reduction, this undergoes oxidation. So the same thing with this one. This one is anode because it is more negative. This one is cathode because it is more positive. So if you are writing a reaction, the cathode starts with an ion, so the lead is being oxidized to form silver. So that is the reaction that comes from that. But just be able to recognize that the cathode will always be more positive than the anode if you are looking at half reactions. Then we have a question here. Determine the standard cell potential given the following. So here you have this reaction. This is the general reaction, and here you are given the half reactions. So you want to determine the cell potential. Especially that you are already given the half reactions, you just need to know which one is cathode, which one is anode. So when you say cell potential is the same as the E cell. So we know E cell is given by E cathode minus E anode. But when discussing, we said that this is anode, this is cathode. This is more negative, this is more positive. So our E cell will be 0.80 V minus 0.13 volts, which is 0.8, which is 0.93 volts. So the E cell of this, the above cell, is equal to 0.93 volts. So let's take note of one other thing. When calculating E cell, you do not really worry about the coefficients. As you can see here this is 2Ag. This is 2Ag, but we did not multiply this by 2, or we did not multiply the E by 2. We never multiply E. So the E should be the one given regardless of the coefficients we are using. So E does not change with coefficients. What do I mean by that? If I have Ag plus aqueous, then plus E minus to give me Ags, the E is equal to 0.80 V. But if I have 2Ag plus aqueous plus 2E to give me 2Ags, E is still the same. The E is not going to multiply by 2. So we need to take note of that. Never multiply E. E remains the same whether you have multiplied by a coefficient or not. So that's how we determine the E cell of a reaction. So this is our answer. But you need to take note of this and this statement here. Consider the following reactions. So we have half reduction reactions. I will just add V here to indicate the voltage. So from this reaction, identify the element to be oxidized. Identify the ion to be reduced. Identify an oxidizing agent and a reducing agent. So when you are given this, the first thing you need to do is you need to know which one is your anode, which one is your cathode. In this case, we know that the anode is the more negative one. So anode is the more negative cell. So which tells us that this one is our anode, then this one is our cathode. So the anode has the element that is going to be oxidized. So anode has the element to be oxidized. In this case, our element is Ba. So Ba is going to be oxidized. So I just said this one oxidized. The ion to be reduced comes from cathode. So ion to be reduced comes from cathode. So this is our cathode, and the ion that is present in the cathode is Au+. So in this case, we have the gold ion. An oxidizing agent. So the ion that is reduced becomes an oxidizing agent. So the ion that is reduced becomes an oxidizing agent. In this case, it is Au+. So Au+ is an oxidizing agent. The element that is being oxidized becomes a reducing agent. So in this case, our reducing agent is Ba. So that's how you recognize the reducing agent, oxidizing agent. You recognize the element to be oxidized, the element to be reduced. So let's look at this equation again. What is the element to be oxidized? In this case, the element to be oxidized is copper. The ion to be reduced, Ag+. An oxidizing agent, Ag+. A reducing agent, copper. So let's look at this line reaction, or a line notation of a cell. The question we are answering is, what electrode is the cathode and anode based on the following line notation? So for you to determine that, you just need to know that this side oxidation is happening. This side reduction is happening. So oxidation happens at anode. Reduction happens at cathode. So reduction happens at cathode. So in this case, we are looking at the zinc 2+ electrode. So zinc 2+ electrode is the anode, while copper 2+ copper electrode is the cathode. What is the change in free energy and equilibrium constant of the reaction shown using the line notation there? So to solve this problem, we need to take note that delta G naught is equal to RT natural log K. But we also know that delta G naught is equal to negative NFE. So N is the number of moles, F is the Faraday's constant, and E is the cell potential. So if we already know the cell potential here. For this reaction, we need to think about how many electrons are being transferred. How many electrons are being transferred? So the number of electrons transferred will tell us what our N is. Now, if we look at this reaction, oxidation is zinc solid to give us zinc 2+ plus 2 electrons. So we are transferring 2 electrons in the oxidation reaction. Reduction, copper plus 2 electrons to give copper solid. So in this case, we are giving copper 2 electrons, which means our N is equal to 2. N stands for the number of moles of electrons that are being transferred. So we can say delta G naught is equal to -2 times the Faraday's constant 96 96485 times the cell potential, which is 1.10, all given in joules per mole. So that is minus 2 times 96485 times 1.1, which is negative 21267 joules per mole. So that is the change in free energy of this reaction. But we know that delta G is equal to this. So minus 21267 joules per mole is equal to minus RT natural log K. So this tells us that natural log K is equal to, these negatives are going to cancel. So natural log K is equal to 212267, that is 7 here, joule per mole divided by 8.314 joule Kelvin mole times, if we are doing this at 25 degrees Celsius, it becomes 298 Kelvin. So 212267 divide 8.314, 298. Again, 212267 divided by 8.314. So natural log K is, it looks huge. Let me do the calculation again. So 2 times 6, 4, 8, 5. So 212267 divided by 8.314. Yeah, so the natural log K in this case is 85.7. It's huge. Therefore, K is E to the power 85.7. So which is again E 85.7, which is 1.66 times 10 to the power 37. So that is the K for this spontaneous reaction. So we'll continue the last part in the next video.